Okay, so we have spoken about, so when I say legitimate descent direction, all that you have to ensure is the angle. Is it less than 90 degrees with the negative gradient? Then you are fine, then it's a descent direction. Okay, so now let us prove, or let us say, let's find the Newton direction. So you're getting the hang of it right now. What is the main tool that we used in the previous development? Taylor's theorem to first order. Now we know that the Newton method is a second order method. So what should be our starting point? Second order Taylor's theorem, right? So let's write that out. So second order. Okay. Again, I want to write f of xk plus epsilon pk. First term, f of xk. Second term, as before, epsilon times grad f. Let's keep it short over here. Okay. Now third term, obviously I am not going to write order epsilon square. Third term, what should I write? The error is epsilon cube, but there is a exact second term that I should write. What is that? There's going to be epsilon squared, okay, divided by 2. Next, pk transpose Hessian pk plus error of order epsilon cube. Okay. So obviously this is also going to be a good approximation as long as epsilon is small, right? It is less stringent than the linear approximation because I am taking into account how the second order term behaves. Okay. Now what do we want? So again I am standing over here, this is my xk, and I want to go to xk plus 1, okay, and I am trying to figure out, is there a smarter direction than what I had just done? That's what I want to do. Okay, now let's go to the real, let's go to the what should I say, dream world. In the dream world, you would reach this point and that would be it. All your troubles would be over. If that were the case, what would be the property of this point if it is the solution? So remember, xk is fixed, okay, right? Okay, I'm getting the correct answer from one student. So this is p. Now p is in my hand. What direction and what length to go? So if I reach xk plus 1 and my problem is done, we had previously spoken about one of the signatures of a stationary point, which was what? Its gradient was 0. If I reach the solution, its signature is going to be gradient is 0. But now just take a little bit of a pause. The gradient with respect to which variable now? Xk is fixed. So what is my variable of that I am optimizing now? P is what I am optimizing. So gradient with respect to P should be 0. So if xk plus 1 is the solution, then I should have grad. Now I am going to put a P over here. Okay. Xk plus epsilon p k should be equal to 0. Epsilon, you can think of epsilon into pk is the thing that I am optimizing. I mean, you could absorb it into pk also if you wanted, right? Since stationary point. Right. So the logic is quite common sense, that should see what the goal is. The goal is to reach a stationary point, right? Now let's take our Taylor's approximation over here, and I want to use this thing that I have derived over here. So what should I do on both sides of the equation? I can apply gradient with respect to p, right? Then I can use the second property. Okay, so when I do this, grad p f of xk plus epsilon pk, okay, and grad p of the whole expression over here, okay. Now this term will be equal to 0, as we said I have reached a minima, okay. Now let's look at the first term over here. What is grad p of the first expression, which is this red term over here? You could answer this if you were in class 11. Do you see the variable p anywhere inside that expression? So it's derivative with respect to something that is not even there, so this has to be 0, right? What about the second term? Epsilon grad fk. How do we do this? Remember grad fk pk. What is that going to be? Grad fk 1 p1 plus grad f2 p2 dot dot dot, right? Or if you want to be even more explicit, this is going to be df by dx1, df by dx2 and so on. And now when I take partial derivative with respect to p1, p2, what will I be left with? Df by dx1, df by dx2, basically grad f is what I am left with, right? So this is the second term. What happens to the third term? We had a little bit of practice for this term. Right, but what is the, before you give the final answer, what is the concept we are using? Supposing I give you, remember we wrote the derivative of this guy, we split it as two functions and therefore we use what? Product rule. And here we have taken gradient with respect to x. Now I have a similar situation, I have some expression in the variable. What order is it? Is it 0, 1, 2 or 3? In the variable p, this expression is what order? It's second order. So I can split it again as, I can write it as one term and another term. So this is very nicely product rule. Product rule, I just have to look up the formula, we had derived it explicitly. So this 2 will go away. What will I be left with? Epsilon squared. Remember, what was the gradient of this guy? Oh sorry, there was no 2 there, it was just this, okay. A transpose plus A times x, okay. So now when I take this, is there any special property of the Hessian? It is symmetric, so its transpose will be itself. So that half, what will happen to that half? A transpose plus A would be Hessian transpose plus Hessian, which is 2 times Hessian. Therefore that 2 goes away. I am left with epsilon square Hessian and what? P, right? So as long as Hessian is positive definite, it is legal for me to invert this expression. If I left multiply by Hessian inverse, what will I get? Remember, these are matrices now, matrices and vectors, we are working with that, right? So for example, this expression over here, what is this? A scalar vector matrix. Grad f is it's a vector. This guy is, Hessian is a matrix and I am multiplying by a pk is a vector. So matrix into vector is going to give me a vector. So when I have to be careful when I move things around. That's why I said left multiply by Hessian inverse. So what am I going to get? Inverse. What else is left? Grad fk, right? That's all that is left. Grad fk. Epsilon is a scalar. It can go any which way it wants, right? So that's why this is important in the beginning to get this practice. Left multiply by L squared inverse. You cannot mix up the order. Right? Now the right hand side, the inverse of a Hessian is a vector or a matrix? It's a matrix. Matrix multiplied by vector, vector, and pk was supposed to be a vector. So at least what we would do is, it's called, you can call it dimensionality analysis, or you could also call it the idiot check, right? That it's, I haven't made a stupid mistake, so this is correct. So this is right, this is our Newton direction. This epsilon you need not worry about. I could have absorbed epsilon into pk also. So what is essential is del squared f inverse, right? This is called the Newton direction. And the reason I am being not so careful with the epsilons is because right now we are trying to figure out direction. We need to figure out step length anyway, right? So let me just get the direction right. Right, so this is straightforward use of second order Taylor's theorem. Oh yes, that is very important. Sorry about that. There is a negative sign over here. Yeah. Yes.
But the combined variables are optimizing the epsilon variable. So pk then if you want to reach.
Correct. So I was anticipating a question like this. So what I did here was I split. I could have also written this as some new variable qk, right? I could combine epsilon and pk into a new variable qk and done the whole analysis in terms of qk instead of pk. What would have happened in that case is that this annoying 1 by epsilon would have gone away. I would have got this expression over here. Correct. So the question is, how accurate is this? Now, as I mentioned, we are splitting the direction. It's alpha multiplied by pk. That's what gets me to xk plus 1. So once I get the direction, it's up to me. I could even normalize it and talk about a unit vector. And in the next step, then worry what is the step length. So we're going to split this into two parts. I'm going to talk about the direction first and then the length. There's an extensive analysis of how to choose the step length. So we'll worry about that when we come to it. So the direction is fine. Right? Direction does not worry about the magnitude of the vector. Remember again that this is going to be accurate when in this expression epsilon is small, because the error is hanging out here, epsilon cube. Right? If you make epsilon very large, this Newton direction, again there's no reason for it to be correct, because there is this, when I took derivatives over here with respect to p, this I put 0. I said it's small, but if it is not small, then this whole thing is out of the window, right? So that is part of the game. So yes, question. No. Okay, so question is good. Question is that why did we make this condition? Why is grad p of f of xk plus epsilon pk equal to 0? Now the reason is this is because I am sort of being ambitious and greedy and saying that give me the best possible p. I don't want to make a lousy step. I want to make the step such that when I reach this step, it's optimum with respect to p, and any larger or any less is not good. The exact p, if it gets me there, is that p at which the gradient is 0, right? So it's the same idea. So in some sense one is being very greedy. Okay, so this is the gradient with respect to a direction and not the variable. In a way it is, because for the purpose of this argument, xk is fixed, it's a point. Okay, xk is what? A collection of n variables, and it's a set of numbers, it's not a variable, it's fixed, right? And what is changing over here? P. P is now actually a unknown vector. How many dimensions does it live in? N dimensions. Right, so it is variable. It's just that we should not get fixed on calling our variables to be x and nothing else. Now the variables of this problem are p. I don't know what p1, p2 up to pn is. So I say okay, give me the best p, and that would be grad p. Okay. If you are very hung up on the variable only being x, there is a very simple way around it. I will just rename my xk point. I will call it something else, ak, and I will say now give me the amount I should walk, and I'll call that xk. So then you will take derivative with respect to x. So we need to be flexible and identify what is it that really matters. Over here, xk is fixed, xk plus 1 I don't know. In fact, xk plus 1 is simply linearly related to pk. Right? So you can also think of chain rule over here. If you wanted to take gradients with respect to the x's, they are related by epsilon, which is why this epsilon keeps hanging around over here. Right? But the geometry is the geometry of the problem is clear. I'm at some point, I want to go to another point. What is changing? It's the p's that are taking me from point A to point B. So let me optimize with respect to that. That was the question? Yeah. Yeah. At that point, correct. So once I reach this guy, once I reach the best, choose the best p and reach xk plus 1, then from that point the gradient in any direction is, the gradient is 0. It's not a directional derivative, the gradient is 0. That means when I take its inner product with any vector, the directional derivative is going to be 0. So that is what I wanted, right? Because directional derivative was what? Inner product of the gradient with your direction of choice. In this case, it's going to be 0 because gradient is 0. Okay, so now a very important question. Are we done? Is this enough? It's a necessary condition, yes, that's one way of putting it. But yeah, so what is the sufficient part? Yes? Correct. What we just spoke about a few minutes ago. We have not verified if the angle is right. In other words, we have not verified if this Pn is actually a descent direction. For all you know, we did a great ascent. At the top of the peak also grad is going to be 0. So we have to verify if this was a descent direction, right? So let's put that down. And we don't have to remember any formula now. What do I have to say? That the angle with, if I take the inner product with grad f, what should the result be? With the gradient. Okay, so let's write this again. Oh, let's go back to our diagram over here. So what should be the angle with this guy? What should be the angle with grad f? Greater than 90. That means the inner product should be less than 0. That's what I want, right? So Pn transpose grad fk, this should be less than 0, right? So implies that, now let's put this in over here. Now one thing, let's make our life simple. Pn transpose grad fk is the same as grad fk transpose Pn, right? A transpose B is B transpose A. So this implies that grad fk transpose minus del squared fk inverse grad fk is less than 0. Okay. If I want to move a minus sign to the other side of the equation, what happens? The inequality flips, right? Most common source of silly mistakes. So I have fk transpose grad f squared inverse grad fk greater than 0. What does this look like? This is of course a quadratic form in grad fk, but does this look like a familiar condition? Right, this implies, so if del squared f is positive, definite, is true, right? So for the Newton direction, I have the expression for the Newton direction, which is over here. This is my Pn. And the second requirement is that it should be a legitimate descent direction, which happens only if del f, the Hessian is positive definite. If, for example, the Hessian ended up being negative definite, what would our conclusion be? We have ascended. So it's like the really difference between day and night over here. Okay. Now there is, I'm going to anticipate an objection over here. Is this a stronger requirement or is this a stronger requirement? Demanding that the Hessian be positive definite is a stronger requirement, because even if, let us say, the Hessian is not positive definite, at some special point in space xk, it could happen that this is satisfied. It could happen, right? So even so, if you are sort of, as they say, flying by the seat of your pants and you use the Newton method even when the Hessian was not positive definite, it may work sometimes, because locally at that point it may happen that the curvature is such that the Hessian, such that this expression is greater than 0. But it's a very, very dangerous strategy to follow, because you never know, when you jump to another point, this expression may not hold true, right? So the standard way is make sure that the Hessian is positive definite, okay, and then work with it. When we go into Newton method in detail, we will talk about tricks to make it positive definite if it is not, in an approximate way. Okay. Yes, question. The first one is the actual condition. That's what I'm saying. The first one is the actual condition, which is a subset of Hessian being positive definite. So, correct, right. So okay, that's precisely what I was saying. So supposing there are some points in space where the this expression is true, right? This grad f k del squared f inverse grad f k is greater than 0. So in that case, what is a true statement? That the Newton direction is a legitimate descent direction. So if you were checking at each iteration, you could use that. Okay, without needing the Hessian to be positive definite everywhere in space. But as I said, that's a slightly dangerous strategy to follow. But people do kind of hodgepodge solutions. So when it is positive definite, you do Newton. When it stops being positive definite, what would you do? Switch into gradient descent, conjugate gradient or whatever, right? So all sorts of things are possible. Remember, I mean, in that way, optimization of non-convex functions has a lot of scope for creativity. No one says that you cannot do this, right? So good. So we have verified this condition, right? So that kind of completes the derivation for the Newton direction. Okay. Even if you take this is the second derivative test, no? You want to state your question again? I think you got. You're thinking of the second order conditions for the point being an extrema, where the sufficient condition was that the Hessian should be positive definite. So yeah, right, they are related. That should, the sufficient second order sufficient condition was that the Hessian should be positive definite, and at that point this Newton direction is correct, right?
This is, I mean, I think this is the conditions required for the direction being a valid descent direction. But if we are imposing that xk plus 1 is, then it's a minimum point.
Then you should check it once you reach that. So you're saying that once I reach xk plus 1, anyway I need to check whether or not, first of all, I should first check the first order condition. Is it a stationary point? And then I have to check whether, if it is a stationary point, then I should check whether the Hessian is positive definite at xk plus 1. He's right. So this is a condition at k, right? At the descent direction at xk, when I'm trying to figure out whether pk is a good direction, I need to check, first derive whether the Hessian is positive definite. If it is, I can use the expression, and then this expression also comes. Actually, let me just correct my previous sentence. For this to be a Newton for this direction to be valid, I don't need the Hessian to be positive definite. It should just be invertible. I could have a collection of negative eigenvalues and positive eigenvalues, the matrix will still be invertible, right? So in deriving this Newton direction, I need not have Hessian to be positive definite, it should just be invertible for this to exist. But here is where positive definite comes in.